told me what should we do instead of just following.
We're doing it. Sorry? No, no. And it's like with the stream, there's a little bit of a delay, so when you look there, it's...
Okay,
Don't look there. You're gonna
when you look there, you'll be confused.
Well, nothing will be like Freudian stuff. That was dizziness.
I wish I was there for that bar you set for me.
No, it was really bad. So I didn't want to be there.
I can always appreciate a low bar spot, so I can feel better.
Well, when Freudian gave a talk here, like the first science night, that was pretty nice because it was about fecal transplantation.
Oh, okay.
Yeah, and everybody likes to talk about poop.
I think I might have been there for that.
Yeah.
I don't remember that.
Ini? Oh yeah, non-alcoholic. You keep it.
Is this already on?
Yeah, it's already on. They turned it on there. Did you have a typo? I am? Oh yeah. Oh, great. I will not work it out. Are we there yet? Where did Hannah go? Sorry. I will continue. It's okay. I did a little crazy. Ah, come on. Last person. Cool. Thanks. Then. That'll be fine. Don't worry. We start? Cool. I remember to speak to the mic. I won't forget. So, good evening, everybody. My name is Joanna. I'm here to kind of introduce to you some of the speakers that we have tonight. So this is, of course, Hansa48 Science Night. I'm very happy that this event can happen again after all that's been happening in the past few months. And this time in a slightly different format. So we also have the streaming online, so on YouTube. And this video is going to be available for the ages to come. So you better do good. So today we're going to have 3 speakers. We have Danielle going first, then Esham, then Aditya. So their talks are going to be quite varied. So I'm very excited about that. First one, of course, about Turkey, because that's going to be a thing. And then we have a bit about AI and healthcare. And then we finish up with some baby space and what we know about it. It's what I remember. Sorry, my memory is like really bad. I try my best. Also, I'm very happy that all of you are here, actually physically. This is really cool. Also, very important person is here, my mom. It's going to be great. Thank you, Mom. You are doing great. So without further ado, we're going to start with Danielle, and she's going to talk about why does Turkey make me tired and other strange tales about tryptophan metabolism. Thank you. Yay!
Thank you. So I decided that I would talk about tryptophan and Turkey today because on Sunday, this last Sunday, it was Thanksgiving in Canada, where I'm from. And I didn't celebrate, so I'm going to celebrate a little bit with you here today by talking about metabolism, one of my favorite topics. Okay, so we're going to start with this, this sort of let's call it an old wives' tale. This is that you eat turkey on Thanksgiving and it makes you tired, and it has something to do with tryptophan. This is how the story goes. So let me first introduce you to sort of the idea of what, basically to know what tryptophan is first. So we have, in this case, the star of our show is turkey. And as you probably know, turkey has lots of protein in it. So if we zoom in here on our turkey, we can see a protein. And it's made up of a bunch of different building blocks. And these building blocks are amino acids. And you can see that one of them in particular is a little bit chunkier than the others. And that chunky amino acid, that is tryptophan. So let's zoom in even further here, and we can see the structure of tryptophan. So this amino acid is a little bit special because it is indeed the biggest amino acid, and it's also the most energetically expensive amino acid to make. We ourselves can't make it, though. So we need tryptophan to come from our diet. And once we get it into our system, so let's take our protein again, then we can break it down. So once we get the protein is broken down, and then ultimately we get tryptophan, which can be used for muscle building and protein production. But this is actually only about, so less than 1% of the tryptophan is used for protein production. And to be honest, I'm not super interested in it. So we're not going to focus on that at all today. We're going to focus rather on the gut and what's going on with tryptophan in the gut. There's 3 main pathways that tryptophan can take once it gets into the gut and broken down into its individual amino acid here. We can have it broken down into serotonin. There's also another branch where it's important for the immune system. And then finally, the tryptophan can also be stolen by microbes, and they do a lot of fun molecular transformations with the tryptophan as well. And if you've heard of the gut-brain axis or have been told to eat more sauerkraut or yogurt because of the bacteria inside, it's partially because we think that the tryptophan that the tryptophan can be metabolized by these bacteria to do some fun things with our systems. So let's talk about Thanksgiving. This is the typical chain of events. You can see here that we have the turkey. And what happens is we eat a lot of turkey on that day. And normally, actually, in Canada, we don't eat very much turkey over the course of the year. Actually, we only really eat it twice a year, for Christmas and for Thanksgiving. So I guess this is how this tale came to be, that, normally we eat food and we don't get super tired afterwards. But on Thanksgiving, we eat turkey and we get tired. 45 minutes after we have our meal, we have to have a little lay down before we go back and eat more, probably. So the idea then, this is a tryptophan metabolism according to my grandmother. We have tryptophan, or you have the turkey. You get tryptophan pretty quickly, and then it's immediately turned into serotonin, and then melatonin, and the melatonin is this metabolite that makes you sleepy. You produce it more at night, and it helps you go to bed at night. So it's a pretty good hypothesis. It kind of makes sense because tryptophan can be broken down into serotonin in the gut, and even serotonin can be further broken down into melatonin. And there's actually a lot of serotonin in your gut. So there's more than 90% of your serotonin is in the gut. So kind of somehow makes sense on the surface, at least, that maybe turkey and tryptophan are making us tired, and that's why we need to have a little lay down after our meal. But that's not the whole story, and that's because of the blood-brain barrier. So when you eat something, the metabolites or the chemicals that you've eaten are not going to immediately just find their way into the brain. It's a privileged area. You don't want just anything running into your brain and causing some chemical chaos inside. So that's why we have this blood-brain barrier. It stops things from going inside too easily. So for example, serotonin is blocked by the blood-brain barrier. There's not really any way that we've found so far that it can easily get inside. Tryptophan, though, it can get inside. but it's not so easily brought into the brain. And that's because this little pathway that brings tryptophan into the brain, there's this little doorway, and the doorway gets jammed with the other amino acids and the proteins that you're eating. So they actually kind of go in there first. So they're first in line in this little doorway, and then tryptophan is a little bit slower to be uptaken into the brain. So let's revisit the turkey hypothesis then. So we have our turkey. Now we know that we have proteins in the turkey, and that first they need to be broken down into the individual amino acids to free tryptophan, the star of our show. And then tryptophan has to cross the blood-brain barrier in order for serotonin in the brain to be produced, and then melatonin, which will ultimately make you tired. And then the idea is that this should all happen in less than 45 minutes, which seems very unfeasible to me. As you can see, it's a fairly convoluted pathway before you can get to this melatonin production, if we're assuming that it's indeed just the turkey that's making us tired. So let's then look at Thanksgiving one more time. So here we have our Thanksgiving meal, and if you think about the typical chain of events, it's not just this big turkey that is present at the table, but you can see that we have a whole lot of other things at the table. And so you have your one plate of food with your wine, by the way, and then you have another plate of food, and then maybe you even have like a third plate of food. And then not pictured here that you can imagine is maybe also playing a role is your family. And in some families, maybe they're a little bit exhausting already, so that could also play a role. And maybe in other families, they're a little bit more like relaxing to be around. So you're feeling relaxed, and you can really just finally take a quick nap after your meal and your red wine. And so the idea then is that it's really probably not the tryptophan that's making us tired, but rather a whole bunch of events, and like the overeating mostly, because the eating is of course very energetically, or digesting is kind of hard to do, let's say, especially when you're eating so much all at once. And that's most likely why we're getting tired so quickly after our massive Thanksgiving meals. So then what's with all of this serotonin that's in your gut then? And actually this is an area of active research. So it's associated with gut peristalsis, and I have this nice video from mice here. So this is the movement of the gut. It kind of helps regulate this process. It's also involved in a vasoconstriction. So this is basically allowing less blood to pass. And there is some potential that there's interactions with bacteria, because what I haven't mentioned is that bacteria themselves, they are influencing the amount of serotonin that's being produced in the gut. So what we don't know right now is whether or not the serotonin that's sort of being produced is also influencing the bacteria inside of us. So that's a general overview of tryptophan, its relation to Thanksgiving or not. And I'm happy to answer any questions that you have or have a little chat.
So I forgot to say kind of what are the rules of the game, but now we're supposed to have loads of questions. So when you have a question, you have to like raise your hand. I will repeat the question so we can put it on the YouTube video as well. And then Danielle can answer. I will start because I'm here already. So my question is, also what I remember of my hormone studies is that there's also like a 24-hour cycle. Is the serotonin involved, and could it also be related that it's just like the time that you eat Thanksgiving dinner or lunch?
So I don't know exactly how the levels of serotonin change over the course of the day, but I do know that we have Thanksgiving dinner at like the same time usually as normal dinner. So I would think that no, that at least that's not the main reason anyway that we're finding ourselves so sleepy after our meals.
Okay. More questions? Yeah.
Okay, that's a great
Wait.
question.
Danielle, can you repeat the question?
Oh, yeah, sure. So the question was, so I've mentioned the relationship between tryptophan and turkey, and whether the question is whether or not there's actually higher levels of tryptophan in turkey relative to other protein sources. And actually, I always thought that this was true, that it was a particularly high source of tryptophan, like higher than, say, other poultry products like chicken. And indeed, chicken actually has higher levels of tryptophan than turkey does. So this whole hypothesis is just like bad from the start. So there's lots of other, like if you are somehow interested in getting more tryptophan in your diet, oats are also a really good source of tryptophan, and cashews, and like there's lots of like plant-based protein sources of tryptophan. But I mean, generally we actually get too much protein in our diets anyway, so it's not like we're running around tryptophan deficient. So yeah, like I said, the hypothesis was pretty, it was pretty bad to begin with.
Okay, more questions? I have additional questions. So, you said in the beginning that tryptophan is used to build up muscles. So is there like how is they call like supplements of tryptophan that you can find in those stores in these gigantic buckets?
You can take, there are the branched chain amino acids. So these are other amino acids that are also like big and bulky. Tryptophan, as I said, is like kind of the biggest, but you, right now, at least there's quite a bit of buzz in the like weightlifting community about branched chain amino acids. I don't think anybody's taking tryptophan specifically as a supplement. You know, some people take directly melatonin, for example. But yeah, for protein building, no, I don't think so. I don't think it's like, it's so, maybe, it's not like it's the rate limiting amino acids, or to use that specific term here in a public forum, but.
And also, I continue. So I heard about this one paper that was studying like the continue on the athletes and the weightlifters and
Okay.
the juiced up people. So they say that this was for marathon runners. They were studying the microbiome of these people that run the marathon and see like what they have anything special. With a high tryptophan, high diet tryptophan also make them microbiome special? Do you know like what would be the biggest differences, and can it be uptake, or there's like an upper limit of actual changes in your microbiome?
I mean, so the real answer is I don't know, because, and the reason I don't know is because I don't know how much tryptophan, so when it's going through your gut, a lot of it, the tryptophan is taken up in the small intestine, and then how much is left over in the colon, where like most of the bacteria are. I'm not sure how much is left there, but the main thing is that I don't know whether or not we tend to be saturated with tryptophan. So whether like I said, we tend to overeat protein. So I mean, if that's true, then I would expect that in our feces that there's actually still a fair amount of tryptophan that's left over, and then just adding more, it's not going to make a difference because our receptors are already busy. they're at maximum capacity, you know?
Okay, last chance. Questions? Yay, another question.
Okay. Yeah, so yeah, tryptophan is one of the essential amino acids, so we really do need it from our diet. Yeah.
And the second one is, maybe can you tell more about this blood barrier? Like how does it work?
I mean,
Can you repeat the question?
Oh, right. Sorry. So
Sorry.
first was was whether or not tryptophan is an essential amino acid, and indeed it is. And then whether or not I can go into more details about the blood-brain barrier. And I guess that would be a little bit more in depth would be, I guess, required, because there's a lot of different receptors that are So we can like stick with this idea of like a doorway. So there's a lot of different doors that let in different like chemicals or like amino acids. And they all have a particular like lock and key system. And so unless you have, the idea is basically that only the kinds of chemicals that have the key can be let into the blood-brain barrier. So that's sort of a very cursory overview.
Yep, another.
Just because perhaps there might be a misconception or misunderstanding, sorry, could you please in one sentence just clarify or explain a bit more what is an essential amino acid versus what is a non-essential amino acid?
Sure. So the question's, can I clarify about what is the difference between an essential and a non-essential amino acid? And the difference is basically, so non-essential amino acids, we can make them ourselves. Whereas essential amino acids, they need to come from an exogenous, so an outside source. Usually our diet, and usually the amino acids are coming from the proteins we're taking, or the branched chain amino acid supplements that the gym stars are consuming.
Okay, any more questions? Oh, there's a flute. Very nice. So maybe we go for our next speaker. Thank you very much, Danielle. That was really nice. And now we're gonna have, thanks. We're gonna have Esha. And can you, there you go. You're an informatician, you can do this. You're IT, right?
Yeah.
Yeah. But there weren't any questions in like the YouTube thing? No. Seems okay.
That's mine? No. This one? This one.
I did spell your name correctly, so.
Yeah.
So maybe let me introduce you first with the correct title. So this is Esham. Esham, also a colleague at our institute, is currently finishing up his PhD. No pressure. And today he's going to talk about artificial intelligence and healthcare. Is it a utopia or a dystopia? So thank you, Esham.
Yeah, thank you very much for the nice introduction. And
Nice.
Yeah. Yeah, so I can promise you this is not going to be as colorful or as pretty as the previous presentation. So just to, set the expectations. So, I mean, I really love, or I would really want this talk to be more like an open discussion, not like one standing and the other people are listening, but I would really love if you can give me feedback during the process, or if you can interact with me during the presentation. So the idea is we are gonna talk about artificial intelligence. Yeah, okay, no, yeah, much better. So yeah, so the idea is we are gonna talk about artificial intelligence and about healthcare. So I think a fair question to start with is basically what is intelligence? So if you're gonna talk about the artificial form of it, what is intelligence? And I would really love to direct this question to the audience. So what is intelligence? How would you define intelligence? What is for you intelligent? Yeah, please feel free to answer. Like, this is really a question directed to you. It's
Something that can solve a complex problem.
okay, solving problem, that's one thing. What other like situations? So one answer, solving problem. What else?
Handling people.
Handling people, that would require also a lot of patience. Yeah.
Learning.
Learning, that's one thing. What else can an intelligent system do? Remembering, a memory, so you can basically, you don't do the same mistake over and over again. Some people like do this. Anyway, what else? Comprehending stuff. I mean, well, it really depends upon how you define independence, but yeah, we can say that. What else? So we have understanding, memory, dependent, maybe adaptation as well. So the more you think about intelligence, the more you discover how subtle it is to really define what an intelligent system is. So let's go to the dictionary. Dictionary is really good in answering these questions. So, well, depending upon which dictionary you ask, you would get a different answer. So if you go to the Oxford Dictionary, it will be defined as the action or fact of mentally apprehending something, understanding, knowledge, comprehension of something. So we have the understanding, we have the knowledge. No one has like mentioned that. And,
Learning.
I mean, we are gonna have a debate about that, knowledge and learning, and then comprehension of something. So that's one mechanism. A second definition, sorry, it's from the Cambridge, was like the ability to learn, to understand, and to make judgments or have opinion that are based on reason. I would really love to add here logical reason, but it's reason. A third definition, according to dictionary.com, it's like capacity for learning, reasoning, understanding, and similar form of mental activity. So you see that per se, the definition of intelligence is really difficult because it's so fluid. Like you can't really have a specific definition of what's intelligent and what's not intelligent. But a common theme that we can, like, you know, one facet of the problem or one facet of the situation might be, okay, so ability to learn, right? So we need to really define now what is learning. So what is learning, guys? We are gonna go for a long night tonight, so.
Taking up new information.
What?
Taking up new information.
Taking up new information. Other definitions for learning. Adapting. So you see something, you know, like that was a very bad idea, I shouldn't do it again, so that's learning.
Use that information in future.
I mean, yeah, I mean, that's really on the borderline of learning and planning. You know, like learning is, yeah,
It's
but
like
you can,
applying what you learned.
somehow. So, what else?
Something that you didn't know before.
And now you know it. So that you acquired knowledge in the process. Yeah.
Memorizing.
Is memorizing equal to learning? Okay. Any other like ideas?
Finding patterns and principles.
Yeah, I mean, yeah, also like on the borderline between like, you know, like, because you might argue that you need to learn something in order to be able to find this pattern. So, yeah. So you see that it's really difficult. Let's see what the dictionary has to say. I love dictionaries, they are really good. So you have these two definitions. I just put them together because they're really like similar. So like the action or fact of mental, oh, that was a bad copy paste. The activity of obtaining knowledge from Cambridge. And there is this definition from dictionary. It's like knowledge or practical wisdom gained from what one has observed, encountered, or undergone. If you compare the definition of Cambridge to the definition of dictionary, you're going to see that they really approach the problem of defining learning from different perspectives. One of them is like obtaining knowledge. It's like you open a book and then you learn some stuff about something you don't know. But the second one is really more like something that experience, like stuff you do it yourself, which means that our ability as human to learn is not like as simple as you might think it is. We learn different stuff, we learn from different facets. So that means that the problem of intelligence and learning and, you know, understanding and consciousness itself is really difficult because it's really difficult to grasp. You can't really define it this way. I mean, if someone here is interested about the topic, there is one book called Philosophical Investigation, and it's really a nice book if you really want to dig deeper into this. But now, so the topic was about artificial intelligence. So welcome to the machine. So the most active part now of artificial intelligence, or the stuff that's making really fast progress, is machine learning. And machine learning is a field that is, well, growing so fast. And it's really like you are using it every day in your Instagram, in your Facebook, in YouTube recommendations, in your Amazon recommendation of product. So wait until the Black Friday. I think it will be fair enough to define what a machine is before we can continue. So I just like today morning, I just typed in Google and what is a machine, and I got this fancy picture. And exactly. At the beginning, it looks super fancy, but if you just look at the details, like it's really one of the... Exactly, it's really one of the most stupid pictures I've ever seen in my life. Because if you really just pay attention to the detail written there and just like, you know, avoid the... It's really simple. It's like, this is not machine learning. So if people have the impression that this is machine learning, it's not. This is not what machine learning is. This might be what a machine learning is. Machine learning is basically a class of algorithms, tools. And these tools help us to solve different problems. So the machine learning really, like a term started in the 50s where we want to build like machines we are going to discuss in a second. But these machines should be like, should learn by themselves and should learn to solve problems or to address challenges. Usually they are, roughly speaking, classified into 3 branches. So we have supervised learning, where you like have an input, and then you have your machine, and you have an output, and you are supervising your machines. Like, here is the input, here is the output. Please learn how to map from the input to the output. You can have also unsupervised learning that people here, like who do bioinformatics, use it a lot. Dimensionality reductions, clustering, like people love it. There is also a lot of generative model there. And where my heart lives is going to be in reinforcement learning, where you basically, because it's a little bit philosophical, you build an agent, and then you try not tell you like, I'm not gonna tell like my machine what to do. I'm just gonna like, if you do this, this is gonna feel good, this is gonna feel bad. So you have the reward and the pleasure, and the machine is just like any learnable system, following the reward hypothesis. I just wanna do stuff that make me feel good. I wanna have this kind of reward. So there is a lot of, it's really fascinating to talk about reinforcement learning. Because of time, I'm just gonna restrict the talk today to the supervised learning, where we are gonna, you know, talk about. Yeah, next edition, reinforcement learning. That will be so much fun. I can show you my code, actually. No. I mean, it's Python code, so it's not that bad. OK, so let's start with supervised. Here we go, the devil line the details. So most of the machine learning is based upon artificial neural network. So I think it's fair enough if you want to study artificial neural network to see how they are really similar to like neural network. And if you want to study neural network, then we want to study basically what is a neuron. OK, so people here that doing neuroscience, please forgive me for what I'm going to say. We can really abstract a neuron into like 3 different parts or 3 different steps. I think I should not go this. You should not go there, yeah. Yeah, I don't have a point. No, don't worry. I did this mistake before, so that was machine learning in action. Yeah, learn it from mistake. You can really take a neuron, and then you can abstract it into like 3 parts. So basically, in a very, very simple way, you have the dendrites, you have the body of the neuron, and then you have the axon. In a very simple, like, you know, definitions, the dendrites here of the neuron basically receive input, and then they are being integrated somehow into the body of the neuron, and then based upon the integration of the stuff, you produce the signal from the axon. Okay, fair enough. By the way, as a side note, if someone here, like most of the drugs, like, you know, not like medicine, like drugs, that, you know, like the opioid, for example, like work on receptors that are here, such as like morphine, heroin, other like stuff such as the benzodiazepines, which basically like Xanax that people use for sleep. I'm so happy my mom is here. Thanks. Yeah, so these medications work in these receptors, and they just change how they perceive signal from the world. Anyway, so this is how a real neuron, roughly speaking, looks like. People of neuroscience, forgive me. And then we can really abstract it in 3 steps. We have the input, it's being integrated, and then produce the output. So if this simple model is, we can abstract a neuron, then let's try to abstract it in an artificial neuron. And that's how we are going to do it. So we are going to have the input. We are going to call it from x1 to xm. So that's the input that goes to the dendrite here. And then we are going to weight each one with a weight that we can learn. So it's a learnable weight. And it goes like weight 1 up to weight n. So each input has a specific weight. The neuron will have a bias. And what happened is we are going to have the input. We then multiply it by the weights. And then we sum it over. We give it to something called activation function. And this is the output. And yeah, that's how you build an artificial neuron, roughly speaking. OK, so yeah, that's an artificial neuron. What about these activation functions, and how do they look like, or what do they do? These functions are really interesting for one simple reason. Let's go here. Can anyone just point me, like, which part is interesting here? Like, I mean, it's not like we are not playing this for money, so you can guess. We can play it for money if you want, but you can like choose a part. Like, which part here do you think is the most interesting?
Synaptic weights.
Exactly, synaptic weights.
I don't know why.
And that shows that it's really difficult sometimes to beat randomness. Yeah, I mean, the point here is like these weights are going to be learnable. So the neuron are going to basically, you can really adjust how the neuron produces an output by just playing with the weights. If you increase the weight, change the weights, then you can change how the neuron's gonna produce or decrease output. So what we wanna do when people speak about learning in neuron is we want to learn the weight of a neuron. Okay. So we can really abstract them, and we can abstract a neuron into something that is called a learnable function. It's a function that can learn. Learning here means changing the parameter, okay? So to give you an idea, we have to define a little bit what is a function, so just a small refreshment. A function is a map. You give it an input and it gives you an output. So let's look at this function here. So the input is gonna be like any number that can go from -3, -2, -1, 0, 1, 2, 3, and then it map it to 0, 1, 4, 9. Okay, question of the day. Can you guess a function? Which function do this?
Square.
Exactly, it's a square function. You know, if you plot it, it's this function that has like an open pole. Yeah, here is our lucky function, fx equal x squared. Take an input and then produce you the square out of it. So usually in machine learning, you can see a lot of equation, but this is really the most equation that people use. So an artificial neuron would either have like a sigmoid function, tanh function. These were like, you know, the good but oldies from the 70s and 80s, but now no one used them, at least not in the main body of the network. You have the ReLU and the leaky one, but I mean, frankly speaking, don't really focus about the details because there is a lot of them, and maybe these two are the one that's being used the most. But just to give you an idea about a neuron. Now the problem is, like, neurons are awesome. Like, I love them, like, I love dictionaries. They are, like, super cool. But the idea is, like, one neuron is not enough. You really need a lot of them. Because, like, think about human. Like, you don't have one brain. You don't have one neuron. So, I mean, you have one brain, but you don't have, but in that brain, you have more than neurons. Yeah, I hope so. Well, it depends on how we define brain and mind. But anyway. Okay, so usually what people realize was, like, okay, we can really do a lot of interesting stuff, or we can do a lot of like fancy stuff if we connect neurons together. So instead of having one neuron, if one neuron didn't work, just keep adding neurons. And that was the approach. So we start adding neurons. And hence, instead of having one neuron, we have now a lot of neurons. And these neurons are like composed or combined, merged, choose the correct word you want to put here, but into a network. And the idea was we are going to have an input layer and then an output layer. So we take the input, map it to the output. But then we know the problems, like, you know, if something feels good, just keep adding it. If we had one layer of neuron, the performance goes up, then let's just keep adding more layer. And then it's going to be a deep neural network. And hence the term deep neural network emerged. Actually, it's every like neural network, if you check the news, like deep learning, and deep neural network, the techniques were basically developed in the 80s. But the problem is we don't have computational resources to just run them. So now we have GPUs, which are amazing, and you can just run them. This is called a feed-forward neural network. So this is one way to arrange a neural network. You can go like more fancy and have something like this, which is called a transformer neural network. Like, it's one of the like hottest topic now, like people using transformer all over the place. And you can have different way to arrange a neuron, but the principle is going to stay the same. You just have a neuron that has weight that can learn, and then you combine them into a neural network. Oh boy. Now, how do they learn? Now, let's think about it this way. You have built this kind of fancy, super big machine. Like, you know, a lot of neurons connected, and you have like a lot of computational resources, you can build it. How do they learn? So in a supervised way, when you build them, you need weights, right? You need to connect, so you see this synapse, you need to come up with weights that connect this neuron to this neuron, this neuron to this neuron, this neuron to this neuron, so the network can function properly. The problem is, you don't know the weights. Here is really the problem. And what we really want to do is we want to learn the weights of this network. Like, this neuron is connected by 0.25 to this neuron, and this neuron is connected by 0.34 to this neuron. This will be the optimal weights to connect the network. These are called the weights of a network. So we want to learn the weights, and how we learn them. That's a long story, but we maybe can do it in the next presentation. But the whole idea is you come up with something called the loss function, and then you use calculus from the high school and the chain rule, and then you can basically minimize, you can adjust the weight to minimize the error made by the network and the predictions. Like, you have the machine, and then the machine's like predicting something, and then you compare it to the truth. Oh, I made a mistake. This is a mistake. I'm going to adjust myself to minimize the mistake. That's the philosophy.
Okay. Do you ask a question?
That's what we are going to do now. Okay. A lot of cute dogs and cats in one picture. Actually, these are like from my friends. Too much cuteness in one picture. Okay, back to business. The idea is now we want to build a machine, or we want to build a neural network. So at that stage, I think it would be okay to assume they are synonymous. And the idea is we want to build a machine, and the task for the machine is really simple. Is this a picture of a cat? Is this a picture of a dog? And this can be really good, actually, if you are able to solve this. Okay, disclaimer. If you solve that, you can write assume that you are not going to follow a machine learning approach. So assume if you're going to write a deterministic code to solve this problem, it would take you years to do this. It's not as easy as you think, because there is a lot of cats, and there is a lot of dogs, and there is a lot of variability. And depend upon the angle. So coming up with a specific rules from a machine perspective is difficult. So what is the best way to solve this problem now? We'll basically just use neural network to do so. How we are going to do it? So we want to come up with this kind of function that is a neural network that will take the picture and some parameter and give us cat or dog. Okay, any ideas how we are going to solve it? That's for you now.
Fast forward to the next slide.
I really wish this would, I mean, if I can do this in my research, I would have been really productive. Yeah, like, guys, it's just ideas, so. I mean, you are going in the right direction, so it has to go with a parameter. So the problem is, like, we don't know.
Give it a lot of inputs. These are cats, 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 and these are dogs, 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 dogs. And from that, we can be able to qualify whatever the input we have.
Yeah. I mean, you just like follow, I mean, maybe you can follow your approach again?
You have to set the parameters, so you can start with like the size of the ears, the eyes, the nose, and whatever. And of course, if you have, as the other person said, much more kind of data to train on, you will kind of get like the variability within the species.
I mean,
Can you like repeat
Yeah,
the
so
answers? Thanks.
Neha's ideas is like what people have been doing for like ages. And the idea is, I mean, so we have two approaches. One approach is like, well, I'm just gonna take a lot of pictures of cats, a lot of pictures of dogs, and just put them to machine. It's gonna find the statistical pattern of what a cat looks like, what a dog looks like, and then we're done. That's not a lot of work. Neha's idea, the participant idea was,
Neha.
yeah, that in shorts. Anyway, it was like, okay, so maybe we can just, extract the size of the ear, the size of the eyes, like the feature in the pictures, and then we can train a smaller model in doing this. The problem with this approach is like, well, who's gonna extract these features? You would need to hire a lot of people watching cat videos the whole day and just annotate. Yeah. But I mean, this would work with cat. Imagine if you want to do it with the surgery pictures. I mean, these people that watch surgery pictures are really expensive, so you can't really hire a lot of.
We
Yeah.
have a lot of medical students.
Yeah, assume you want to do with a high quality annotation. Okay. Yeah. Okay. So these are two approaches. So the first approach was we're going to do this and then extract features and then just try to learn those features. This was an approach that people tried to do it in the 80s and 90s, but the problem, as we told, is like it's really difficult to come up with like features, and it's really difficult. It takes a lot of manual like effort to extract the features. The second approach was like, take everything and just like learn statistically out of it. And that's basically was like really the killing of these problems, like statistical learning, or we just learn by, by the data we have. So how would you really construct a machine that does this? So the idea is you have a picture. That's easy. You can check my phone. You're going to see a lot of cat pictures there. Then you have a machine. So far, so good. This machine is basically start random. So what we are going to do, we are going to build a machine like this. And these weights are just going to be random. Like, we don't know any knowledge about them, just random. And yeah, we give it to the machine. Well, because the weights are random, then the machine is just going to give you a random probability. Like, what is the probability of being cat or dog? Just 0.5. I don't know, just something random. but we know the label. So we know that it's a cat picture, and we know that this picture is a cat, or we know this picture is a dog. Some human annotated them that this is a cat or this is a dog. And what you are going to do, you do something like called a loss function. The idea is the machine is just going to make prediction. Is it cat or dog? Probability between 0 and 1? I don't know. 0.6, 0.4, 0.5. And if you assume that cats is 1 and dogs are 0, or the other way around, then you can basically quantify how much error the machine has made by just comparing them. You predict it to be 0 and it was 1, or the other way around. You have a quantifiable, you can quantify the amount of error the machine made. So it should have been it should have been 1, you predicted 0.6. It should have been 0, you predicted 0.4. So you have a metric of how much error you made. Now, okay, now we have an error. What we do with our mistakes? We learn from them. So we give this error to an optimizer, and this goes to a machine. And then this process goes over and over and over and over. And then, we keep doing this. Of course, we need okay, so this, take with some salt. You need a lot of data here, and this would correlate with the size of the model you want to achieve, the the number of pixels you are in the pictures, how it's high quality or low quality. There is a lot of details here, but this would be really the bigger framework. The takeaway, have a lot of training data and a good machine, and then you would have achieved state of the art. So that would be the approach. So we can really abstract the way you train a model now, or you develop it, into a very simple 3-step process. I call it the power of abstraction. So first of all, get data, a lot of data. A lot of input, a lot of target data. And the point about the data is going to be a point that we're going to discuss it a lot in the end, because data is expensive, and data is going to be the new oil. Who owns a lot of data can really generate the coolest model. Now you have a data. What you are going to do, you build a model. You have the input, you have the output, and then you have your learnable function. And this function is just going to learn how do I map from the input to the output. I see the picture, is it cat or dog? I see your medical record, are you going to get a disease or not? I see your genetic data, and I see how likely you develop a specific disease, or how likely you die early, die late. Assume that we can learn this from genetic data assumption. And then what you do, once you have the model learned and tested, then you can deploy it. You are going to see a new input, and you don't know, is it a cat or dog? You don't know, is it health or disease? And you can just predict. And how can I say? If you have a good model, then you can have good prediction. If you have a bad model, then you have bad predictions. So the process really, you collect data, you learn from the data, and then you predict using the data. So far the talk was try to discuss from a philosophical perspective, or we try to discuss cat or dog. But I work in an institute for clinical molecular biology, so we have a different agenda than cats or dogs. Is this really useful for the medical field, or is it useful from a healthcare perspective? This was one paper come in 2019 where they basically train a neural network, instead of cat or dog classification, to basically classify pneumonia or identify pneumonia in the X-ray. And the idea is, not really to replace physician, but just to have an aiding tool, which I think is an agreement now that we are not going to replace humans. We're just going to provide a tool that helps them to be better than a machine or a human, but both of them are better. And this was, achieved really, really good performance. We'll get back to this point in a second. A second application that kind of made me super excited, couldn't sleep that night, was this paper coming by AlphaFold, which is, So they basically built the best model for predicting the 3D structure of protein. And trust me, the biomedical field and biotechnology is gonna be wild in the next 2 or 3 years, because just these tools, you can have the 3D structure of the protein, and you can really do a lot of docking. You can try to predict receptor interaction. You can predict the effect of a mutation in the protein. So it's really, really cool tool, and it will really transform our understanding of biology. So this all looks pinky and rosy, and the future is going to be a utopia. But is it really going to be a utopia? And these are the points that we really need to discuss each one of them in a more details. So I think one of the challenges that people are know now, that if you really want to build a good model, you need a lot of data. But then this raises a problem that there is data privacy and there is ownership. Data someone owns the data, and you can just hey, can I just take your data, or not even asking you, I'm just going to use the data to build my model because, well, I have access to it. Like, who owns my data? And what kind of right this person has to do with the data? And if you think about it from a genetic perspective, assume that, like, who owns your genetic data? Is it the company that do the sequencing, or is it you? And if you died, who owns now your genetic data? So, sorry, I mean, I made a good intention. So, so this is really one of the things, and we should really have like a really good definition of like what is the ownership of the data, and data privacy. A second thing is like data bias, and this is really common, something called large language model or foundational model, which is like very big model that basically you get all the text on the internet and then you train like a text model on it, all the text on the internet. And then you start to see a problem that these models learn from data. If your data is biased, your model is biased. If your data contain like, xenophobic, sexist, racist, like, whatever's there on the internet, then the model is just gonna learn it and the bias is just gonna propagate. How do we control this? And this should be an active area of research. Like, if you have a dog, you need like to chain it, but if you have a model, you also need to control it. These models can be huge, and when I say huge, they can be really, really huge. Like, I think the latest one, GPT-3, has like billions of parameters, and NVIDIA just released a new one which contains billions. So there is an environmental cost and the carbon emission cost associated with training these models. You need a lot of computation to train them. A lot of energy will be invested. So what is the environmental the environmental cost of this step? Accountability and legal obligation. So I developed a model that just tried misinformation articles. I mean, it's not me, it's just the models, like go and sue the model. How we can solve such a problem? How do I make sure that the models we produce are robust? So I work in, Manchester and then produce models that work in the machine that was in Manchester, and then there is a group in Kiel that basically work on the different machines. How do I make sure that the predictions come from the machine that was like for the model trained on the data from Manchester would work on my data, because they might be different. The alignment might be different. And this is really a big problem for the biomedical field. Now there is way to mitigate them, like federate learning also, but this is a problem. Yeah, and finally is accessibility. The problem is when these models become super big, then not everyone can train them or can use them because they are so big and you need to have a computational resources that you don't have. So how do we make sure that it's really accessible? So a lot of questions, and yeah, there is also a social impact of this problem. Like, you have the bias coming from social, the model that do the facial recognition, like for some people that are not from European ancestry, they might not be recognized as well. So you can have a lot of bias going on there. With that, I would like to end my small presentation, and I'm really looking forward to discussing it with you. Thank you.
Not so sure about the small, but yeah. So we open for questions now. I will start. Mm-hmm. So I'm very interested in the bias. So because what we learn now in the medical field is that the physician or the people can be biased, especially to identify severity of disease. Huh? Mm-hmm. And what they keep on asking is to have an unbiased way to quantify disease severity. The problem is these models are biased already, right?
I mean, so the models per se is not biased, the data is biased.
The data is biased, yeah. What enters is biased, yeah. So it will not work. It's a dystopia. Or it could be, and this is what I think, that, it doesn't work for all. It does work for some. Yeah. And that's one of the things that, and I would like you to comment on that as well, that there is no one answer to that is general and can be used everywhere.
Yeah. That's a very good question, and like short answer is like I can't give you a specific answer or a specific solution. That will be the most like honest way to say it. But if you how can I say, if you just wanna discuss about it, the question should be like, do you really like want to have a machine or like a model that just work everywhere. Maybe you are happy with a model that
One ring to rule them all.
I really doubt that. Yeah, I mean, I don't think like in the foreseen future that we are gonna have these models. We still have a lot of problems to do this. Like, I mean, even federated learning still also have some kind of, you know, I mean, it's not easy to build a federated learning system.
It's not easy to see if it's a cat or a dog.
Yeah, I mean, you can deceive them. And I mean, there is a lot of things that you can't, I mean, these models have to be seen as statistical learning models. So there is no like active reasoning or, you know, questioning about it. Like they see a pattern, they just try to learn a super complicated function that map an input to an output. You give them the data and you be like, okay, that looks for me like a cat, so it's a cat. So it's not really like there is no active reasoning that you can argue about. Like, remember our first definition about intelligence? I mean, actually, that was a really stupid answer. Then I can go from the beginning.
Very short presentation.
Yeah. I don't know what's wrong with your laptop. I think it's quite old.
Hey, the hate.
Don't tell me it's the last slide, because that will be really, it's the last slide.
Yeah.
Yeah, I just want to start from
You
the beginning.
just went the wrong way, man.
Yeah, I mean, I will solve it, don't worry.
Okay. IT person.
Yeah.
Yeah, you can leave it
Intelligence.
like this. It's okay.
Yeah.
They can see the messy computer.
I mean, so this model does not really perform this. Like, you know, the problem is like one of the most difficult words to define understanding. It's like, what is understanding per se? Where you can really argue that there is an active understanding similar to the human understanding. So this is one of the things, is like, that's why I really love the term machine learning more than artificial intelligence, because I think it's really more appropriate than just like putting artificial intelligence brand and everything. Because really to be intelligent, you really need to have a lot of, you know, abilities that the current machine does not have. Like the ability to make judgments and based on reason, that's a really complicated or like a difficult, you know, requirement to achieve. And there is also one problem, like called the explainability that, or the interpretability. Like, yeah. So it's really difficult to interpret what these model, like why they make a specific decision.
I'm sorry. Okay. More questions. Aditya.
Data diversity solve this problem? And what, if not, why not? If you feed the machine diverse enough data, why cannot it give you an accurate answer?
Yeah, the problem is like it's really difficult to get the diverse data.
Can you repeat the question?
Yeah, the question is like why, if we give it a diverse data, why shouldn't be this? Well, it's really difficult to get this kind of diverse data from different sources and then just train on them. You would need really a lot of them. And for example, for some kind of data, for example, you just don't have it, or you would, the cost of generating the data would be really high. So it's always like there is also an economical aspect into it, because the most expensive part is the data.
So it's not an in-principle problem, it's
No,
a practical problem.
it's a practical problem. It's just like we don't have enough data.
I have a question and then a comment.
Yeah.
So what to start with? So the question is, for these supervised learning type of things, the output is a prediction. It's not this is it and take it as it is, right? It's just a prediction.
I mean, it's a number. It's a probability of a class, for example.
Okay.
So I'm not quite sure I got the question.
I'm not sure if I get that.
Yeah, I mean, so what this model produce, for example, if it's a classification problem, like it's 1 or 0, then you would get a probability like, you know, 0.01 or 0.9 or 0.6. So that's what you're going to get. If it's a regression, then the output is different because the loss function is going to be different. If it's a multi-class classification, then it's a probability over class.
And the other thing is a comment on something that you actually said, right?
Yeah.
A minute ago or something about having, it's no problem having a model that is created for all, like tailor-made for a certain type of people, let's say in the healthcare sector or whatever. But in this era of globalization, I think this would be a problem.
Yeah, I mean, I mean, it really depends. So for example, if you build a model for a CT machine, and the bias is just coming from the machine, not from, for example, the people that just goes in, then this model can work for that particular CT machine in that hospital. But this would be one way to do it. But if that, for example, if the bias is coming by looking at the medical data, or for example, like a problem in the US when they use machine learning to basically predict how people are dangerous they are, and then they just like recommend to the judge how many years this person should stay in jail, you can really guess that if you are black, then you are in a...
Or getting loans from banks or
Yeah, I mean, if you are like from like with this model that predict how many years you should stay in jail, if you are like not white, if you are like from an African American, then you are not in a very good situation. Actually, these models are biased, and it's known.
And healthcare as well.
And healthcare as well. And imagine that these models now being applied to look at your genetic data or your family data and then predict how much you should pay for your healthcare. Would this be fair or not? So really the implication of the model. So I'm not really afraid of like, you know, a machine is gonna come up in the morning and cite it like, you know, the Terminator fantasies. No, we are really far away from this. But really what we can do with this machine, I think there is a company everyone knows, Boston Dynamics, that produces kind of cool dogs and robots. You can really check it on the internet. It's called Boston Dynamics. A lot of like dancing robot and everyone's so cute.
Sounds creepy.
But they just signed a contract with the US military to produce robots that have guns, and then it's gonna join the military. Yeah, so for me, I mean, I think artificial intelligence or machine learning at the moment, it's a tool. And we really need to be really, really responsible with using this tool. So, because it's really start to affect a lot of aspects of our life. Look at Facebook like recommendation algorithm, for example, and what happened with the US election. And look at the spread of misinformation. And we really need to be responsible with like the powerful tool we have in hand. Yes, we have two questions, so ladies first.
It's you, Neha, it's you. You're the lady.
So I'm coming back to the data itself. So you said multiple times that if the model is bad, you will get a bad prediction in the model. But I found that you did not emphasize so much on the data. So you said once, which actually is the heart of the problem in most medical studies, assuming that genetic data can tell you this. So here is my question, is like, first we need to know which type of data we should use, and then we can talk about the model. Like if I want you to like recognize the model to recognize a knee, and I give it like 1,000 or million pictures of an ankle, it's not gonna do it.
Exactly.
You need to know which data to put in.
Yeah, I mean,
Can you repeat the question?
Yes, sure. I think the question can be really explained here. At this part that I'm...
With the ankles.
Yeah, so the idea is when we collect the data, we need to have an input and the output. And we assume that there is kind of link between the input data and the target. For example, like, I mean, the example we have from Neha, if I'm trying to recognize Neha's face, and then I'm having a lot of data from like, you know, cat's face, then this is not gonna help me. So I need the input and the target to kind of correlate with each other. Like there must be like the input and the target should be linked. Like I can't like, how can I say, look at which day of the week it is and your probability of winning the 1,000 euro or found 1,000 euro when you're walking in the street, because there is no statistical correlation between them. So there must be some kind of input output. And in the biomedical field, it would be really interesting. So I tried really to avoid going into detail there and try to focus on the bigger picture of like, you know, recognizing like cat and faces, recognizing images, generating text, because that's relatively easy and we in human can understand it. But just going into like, you know, yeah, which omics data, should we use proteomics or should we use metabolomics, should we use genomics, should we use transcriptomics, which layer would have a great explainability of doing that, not using all of them.
Spatial transcriptomics.
Spatial transcriptomics. Yeah. You had a question?
Yeah, actually, you're dealing quite a lot with AE. So my question is, what's your opinion on explaining the AE? And wouldn't it maybe a way to like understand why models are biased? I mean, there's like quite some ideas from game theory how to explain the predictions in the model.
Yeah. Well, actually, this is really an active area of research, and so I would have to agree that like the data I'm working on, the model I don't develop, like explainability for us is not the top highest priority. So what I'm gonna discuss with you now is not like the most like active work in the field. It's just my opinion. I mean, what we know so far is like the powerful class of model was deep learning model. So you can try other class of model to do the explainability part of the model, but they are not as powerful like, you know, the other machine learning algorithm, they are not as powerful as deep learning. So deep learning give you a lot of power, but on the price of being explainable. So there is this kind of trade-off. Do you want to be like really explainable, or do you want to be like highly powerful in like learning and generalizing? So finding a middle ground, I think, would be like a sweet spot for medicine, but I can't really like, how can I say, help you further in this. Any more questions? I think you had one?
No longer.
Yeah.
I'm not so really part of the science field of it, just for me to give a feeling. For example, when you teach your machine to recognize cancer in pictures taken from bodies, how many pictures or x-rays would you need? Can you like rounds to say, okay, I would at least need over 500, 600, or even maybe 1.5 million pictures for me to understand, okay, what kind or how much data are we talking about before we can even talk about that this machine would be usable in helping to see cancer?
Yeah, well, yeah.
Thank you.
You really choose,
How
well,
much data is a good amount of data?
yeah, that's really one of the most difficult questions to answer, because it's not really, well, actually there is no like really an easy answer to this. So the general rule of thumb, well, more data, better model. So the more you can get, you are in, like, you know, on the safe side. Always more data is good. No, always more good
That's
data is
not-
good.
Exactly. It's like I have a little bit of an issue with it. Everybody always like more data, and it's like, no, it's confusing everything.
Yeah, I mean, what I refer about data. So in the case of imaging, having more images with more annotation, that was for me particularly the case about data. It's like, of course, like I wouldn't be really happy if I'm training a model of imaging. It's like, look, this person eats burgers 3 days ago. Hopefully this will train your model better. So if the data is not relevant, it's not gonna make my life easier. But what I mean here is like having more X-rays is gonna be a better idea. Having X-rays that is correctly annotated by the X-ray physician is also gonna be a good idea.
The inherent assumption of no bias.
Yes. No bias there. Like we try to keep our life as simple as possible. Usually like with the range of thousands, like 10,000, something like this, you are good. But of course, the more data you have, the better you are. And this also means that it would be really good if we start like storing our medical record, the diagnosis. So for the future, we can train model on them. But then we are gonna go back to the first problem, like, do I mean that should I allow other people to train model in my data and to use them for training other models? Do I own them or not? I know there is one company, a startup in California, that you can basically sell your genome, because like some companies like 23andMe, they sell your genome to the pharmaceutical company for producing drug. There is this company allow you to sell your genome, so to say, and it's something like the blockchain. So you can kind of sell your genome, but because you own your genomic data. So yeah, give me more data and I will give you a better model, roughly speaking.
Following up on this question, so is there a bargain between volume and quality of data?
I mean,
If I give you high quality data, do you need less volume?
yeah, but to a certain extent. So, I mean, you can't really give me 3 high quality data and assume that I would build a deep learning model on them. But of course, like if the data is bad, like the model is gonna be bad. And it would affect the quality of the prediction model. But usually what we learn, not from imaging, but from like language model where people try to come up with model that, you know, something called GPT-3 and GPT-2 that just try to predict text or generate text. They usually just get all the text on the internet and they just train the model on it. And they assume that, you know, the model somehow is gonna learn from the huge volume of data.
There was another question.
Yeah.
I would like to go to the details of the mechanics. In the computer, every information is saved as 0 or 1. When we are talking about recognition, are we talking about recognition of patterns of 0 and 1s in the computer? How does an image, or how can an image be transformed into information from the computer?
Okay, that's a nice question. So, Let's go to the cat and dog. Sorry, not here. It's here. Yeah. So how would you represent this picture to the computer? Well, we need a little bit of a technical term, something called tensor. And tensor is like, metrics are like columns by row, but tensor is like 3 dimensions. So there is a depth axis. So you have widths by heights and then depths. And here what you are gonna record, for each pixel you are gonna have 3 numbers. So the first pixel is just gonna be stored like red, blue, and green. So you have like the 3 numbers that goes from 0 to 155 that represent the red, blue, and green, which represent one color. This will be the representation that the machine has used as an integer. So this matrix is gonna be an integer if it's colored. Now, if you want to go to the 1 and 0, then each integer will depend upon if it's integer 32, integer like 8, 16, 64-bit, or going to be presented into 1 or 0 to represent that particular number. So it depends upon, which integer you are using to represent the numbers in that tensor. So it's a lot of matrix multiplication going there and a lot of numbers.
Yeah, you lost me a bit on that one.
Exactly. I mean, if you just look what the neural network is doing, it's a lot of matrix multiplication, between the input layer and the next layer, between this layer and this layer. That's why you do a lot of matrix multiplication, and that's why you use GPUs, or you can use TPUs with like tensor processing units. Some companies even start to produce hardware chips that just design for like solving this computational problem to be more efficient, and they use less energy or less amount of computation to solve it. Anytime.
Okay, so we're gonna have a break now. We're gonna have a break for 15. Sorry. We can meet again in like 15 minutes. Would that be okay? Or at least till everybody gets their beer. Then we continue. Yeah? Okay, thanks. Thank you, Esham.
Thank you very much. Thank you.
Are we sorry? We sorry? Okay, we sorry. Cool. So welcome back. So now if you are on YouTube, you will not see our first slide because of, how you call it? Copyright infringements. But imagine a great picture of Calvin Hobbes. And we go from there. And thank you so much, Aditya, for being here. And maybe you can explain what's going on in the screen first, and then we go from there. Yeah?
Oh, it's just, is this on?
Yeah.
Okay. So this is, I don't know if you guys are fans of Calvin and Hobbes.
Yes.
If not, you should read the script, maybe when it's on YouTube. But right now, let me move on. Okay? So today, I'm going to talk about photographing the baby universe, okay? And what do we learn from it? So for the past 2 talks, we've been talking about some of our human endeavors. So in these final 20 minutes for today, I'm going to get you I'm going to get you to look up to the heavens. Okay? So I'm a researcher actually at the University of Manchester, and I'm one of the people who've benefited from COVID and get to be here with my family and work remotely. Okay? So let us start with how does science actually work, okay? And so the basic idea is that it's an iterative process. You don't have final answers. So you either start with observing or you start with building a model, okay? And then you try to, if you start with observing, you try to model it. Then you acquire the data. You have analysts. Nowadays, you have analysts who would analyze it and who would talk to model builders. And you have to basically complete this circle. And you go around in circles one way or the other multiple times, and you keep refining your models. Okay? That's basically the way science works. I think this is generically true for all sciences. And today, maybe I'll give you glimpses of how it works in astronomy. Okay? So it's kind of like this. You know, you must have all seen The Blind Man and the Elephant. And we are all, when we start studying the universe, are blind in some way or the other, okay? And so the way we interpret the universe has always been limited by how well we observe it, okay? And observing the universe is, we are kind of these men who have some handicap or the other, okay? So now I'm going to just fast forward because I want to tell you the story of the cosmic microwave background. So I'm going to take you through about 100 years in about one slide, okay? So till as recently as 1920, we were still debating, oh, is our universe just the Milky Way, or are there more galaxies out there? Is it bigger? So that was in 1920. Then in 1929, Edwin Hubble started making observations, and then from his observations, we learned that, oh, we live not in a very small universe, actually in a very big universe, which has very many galaxies. And not only that, these galaxies are actually moving away from each other. And as you may have known, that we live in an expanding universe, okay? So that's now been in the common folklore for many, many years, but that will not be the topic of the talk today, okay? But since, okay, so in the last, the universe has grown by about 500,000 times, okay? So we thought that our universe was only as large as a galaxy. Today we believe it's about 1 million times larger than that. Okay, and I'm going to tell you how is it that we've gotten to this story. Okay, so like I said, we are handicapped in many ways, and when you first observe the universe, this is probably the night sky that you're already familiar with. When you look up, and maybe if you've been in one of the darker places, you've seen this Milky Way band, or maybe some of you have been lucky to see through telescopes. Okay, but this is our human inability to see only in a limited part of the electromagnetic spectrum, okay? So for us, we are only having access to the way the universe, to the way the sky looks through our eyes. But today, after many, many technological advancements, we can look at the night sky not only in optical, but in many other frequencies, okay? You can look at them in gamma rays, in X-rays, you can look at them in radio waves, and you can look at them in the microwaves. These are the same waves which heat the water in your microwave ovens, okay? So these are typically electromagnetic waves of order of, which have wavelengths of order of 1 centimeter, okay, and thereabouts. So the point is, so this is our analogy of the blind man, right? So each of us, let's say we could look in gamma rays, we had one view of the universe. If we looked at it in X-rays, we would have one view of the universe. And today, the whole community, the effort is somehow to put all these pictures together to get a refined picture for the universe, okay? So, but one of the key milestones in astronomy has been this particular measurement, and today's talk is going to focus on this, okay? So what is this microwave background? So I don't know if you know it or not, but most of our universe, almost 99% of it, is composed mostly of hydrogen and helium, okay? And we now understand this hydrogen and helium was synthesized when the universe was old, hot, and dense, okay? And people who found this out, actually studied this, also postulated that because the universe was hot in the past, there must have been some remnant radiation from this hot, dense phase of the universe, okay, long, long time ago. Okay, this was something that was postulated by people who were theorizing different models. Yes, okay? And it was in 1978, these two astronomers, they were working with this telescope, and they were just doing some studies, and they found a constant hum in their system, okay? And they were not quite sure what it was. Was it their electronics which was going crazy? It had some noise. Was it pigeon shit? They cleaned pigeon shit of their telescopes. But no matter what they did, and no matter where they pointed the telescope, they had this constant hum, okay? And it was then confirmed that this was actually, in fact, the same microwave background radiation that people had postulated. And these people then won, actually, the Nobel Prize for this observation in 1978. Okay? So this was just the mere detection of this radiation from the hot, dense phase of the universe. But we have come a long, long way since then. Okay? So now note that this happened in 78. So that's roughly 70 years from the time when we were still thinking that Milky Way is the size of our galaxy. Okay? Just keep those time frames in mind. Okay. So what do we know today? So this is still an intermediate step. What we know is there was another experiment called COBE, that is the Cosmic Background Explorer. That was the name of the satellite, okay? And it was led by these two scientists, George Smoot and John Mather. And in 2006, they got the Nobel Prize, but the results were delivered much before in the 90s. And what they measured was two important things. They could get electromagnetic characterization of this radiation. So they found out that it was actually a black body. And for those of you who know black body, this is one of the best known cases of black body measurements that we know till date. So the error bars here are, by the way, like these are 400 sigma error bars and not 2 sigma error bars as is usually shown, or 1 sigma error bars as are usually shown. Okay, so these are 400 times the error bar. For statisticians, they can appreciate this better. For others, ask me questions later on. Okay, so not only, so this is just the monopole. This is just this constant hum coming from all directions that we look in. But what they also noticed was that, but there is this dipole kind of, there is this kind of pattern on the sky. So, okay, first of all, what are these maps of? So given that you have this black body spectrum, what you can do is you can make maps of a temperature. You can think of it like making a heat map of the universe. So you point your telescope, it's like a thermometer. You point in each direction and you ask, what is the temperature of the sky? Okay? So if you look at it on the whole sky and you look at it with a poor instrument, you will say, okay, the temperature of the sky is around 2 degrees or 3 degrees, okay? If you look at it a little more carefully, that is, if you make a finer instrument, you see that, there are these patterns which looks like it is much hotter in this direction and it's much colder than the other, okay? This is if you go to millikelvin precision. And now if you go to microkelvin precision, you actually start seeing these anisotropies, okay? And we're going to get to what these anisotropies are in a bit. What you see in the center here, this red bright thing is actually our galaxy. It's just the hot gas and all the various phenomena that are happening in our galaxy, and they're emitting a lot of light. This is just that. We do not care about this so much. We care about what is happening here and here, okay? So the Nobel Prize was given for this measurement, which is one of the most precise measurements of the spectrum, and detection of these anisotropies, okay? So what are these anisotropies in the CMB, okay? So that's the story that we're going to get to next. So when the universe was hot and dense, all matter that we know, everything that surrounds us, was not in this state. It was actually in a state of plasma. That is, all of it was stripped down to its bare bones of electrons, neutrons, and protons. Okay, and that was coupled with a sea of photons. So actually, when the universe was very, very young, the dominant species in the universe was these photons, or just light. Okay, and they were very tightly coupled. So you can literally think of this plasma as being a hot gas. And as we all know, hot gas tries to expand. Okay? But then there's gravity, which tries to make it collapse. Okay? So because you have these competing forces now, you basically have this fluid which is kind of oscillating. And if you can think of it like this, you can think of it like there's some plasma and there are these waves which are going around. But as we now know that the universe has been expanding, so now we know that as gas expands, it cools down. Okay? And that's exactly what happened in the universe. As the universe expanded, the gas actually cooled down. And once it cooled down enough, you could actually form neutral atoms. Okay? And the photons were no longer talking to the normal matter in the universe, and there was no longer plasma. The photons were free to go their way, and the matter formed neutral atoms. Okay? What then happened was these oscillations, as the universe expanded and the gas cooled, it froze. Okay? And when it froze, there are places where you were left with more matter, and there were places where you're left with less matter. So if you think very simplistically, if you look at this cartoon diagram, so let's say this is a mixture of many waves of different frequencies, but let's say we look at one particular one, you will see that you have matter clumping in the clump, in the troughs, and then you have these hills where there's not so much matter. Okay? And where there was more matter, there was actually more density of photons, because the matter would not allow the photons to go away. And where there is less matter, the photons and matter would not talk to each other as much. Okay? So now, from this picture, you would expect, so when I look up in the sky, there should be places where it should look hot, and there should be places where it should look cold. Okay? So that's exactly what we have been measuring now for nearly 2 decades. This is one of the most recent measurements, which was run by the Planck Satellite. It was a European mission. And it basically mapped the microwave sky in these 9 frequencies, starting from about 30 gigahertz to around 900 gigahertz. Okay? And what you see over here is that the patterns in the top and below are quite the same, but what is changing across these panel of plots is how strong the galactic emission contamination is. Okay? So the reason we need to measure, so I will tell you why we need to measure in these many frequencies, but basically you have a satellite which is sent to space, and it basically scans the whole sky to make these maps, and the reason you see these egg shapes over here are basically a way of showing the sphere on a 2-dimensional plane. Okay? Okay, so like you can see that you saw a glimpse of how the sky would look in optical, and this is actually how you look at it in around 300 gigahertz. Okay? All this emission that you see is dominantly from our own galaxy, but at high latitude, these small fluctuations that you see are actually of primordial origin. Okay, so basically, once you have all these maps, what you can do is we know now properties of, we know the emission mechanisms in the galaxy. We know what are the properties that we expect for these anisotropies because we've measured the spectrum so well. Remember, I told you something that we measured, the plot that I showed you with 400 sigma error bars. So you can combine all that information, and from these maps, you can actually extract a map like that. Okay? And this map is actually a projection of the state in which the universe was about 13.5 billion years ago. Okay? That's quite literally true. So this is literally a picture of the universe when it was about 13.5 billion years old, and we can actually take this picture today. Okay? So things to note over here is that these fluctuations are of the order of 300 microkelvin. Okay? So that's, the microkelvin is, I hope everybody understands what that means. If you don't, then we get to it, okay? Oh. All right. Okay, moving on. So given this picture, many of us, or many of you would have seen this this version of the universe that we now think that our universe is composed of 73% of something that we call dark energy, about 23% of dark matter, and the normal matter that you and me are made of is only composes about a mere 4% of the total content of the universe. Okay? So now the question is, how did we get from this picture to this story? Okay? And in the last few minutes, I'm going to tell you how is it that we do this. Okay? So when you look at, this is the sky, and I've just taken a slice of the sky. And what you can actually measure is the sky, these patterns are actually, it's a random field. There are no specific patterns in there, okay? It's just a Gaussian random field. And what we measure is actually the variance of this field as a function of wavelength, okay? So what actually is conventionally plotted is the inverse of the wavelength. So like you can see, for low multipoles L, or the inverse wavelength, when that inverse wavelength number is small, here you see that there are long wavelength features on the map. And as you go to larger L, you see that these features become finer, okay? So basically, this is telling you how much power is there in modes of various wavelengths, okay? And what our models allow us to predict is this quantity. Our models tell us what are the statistical properties of this field, which is captured by this yellow curve, which is showing you how much power is there in the different wavelength modes of the measurements, okay? So what can we do with this? So let's say we now have this is not a model which you can write down on paper. It's a computer model, okay? It's a computer model, and you can tell the computer model now, when you simulate a universe, you can say, let me change the amount of dark energy in it. And if you do that, then you see that this curve wiggles around a little bit. You can say, let me change the amount of normal matter that we are made of. Then you get different curves, okay? Or you can say, let me change the cold dark matter, and it'll change the graph in a particular way. So what is done is that once you have this measurement, you actually try to vary all of these parameters simultaneously, and you try to constrain them, okay? So let us not spend too much time on this slide, but I just wanted to give you a glimpse of some of the details. So for example, let's look at this. If you look at this plot, so this is omega baryons. Baryons is the normal matter that we are made of. And this is the cold dark matter, okay? And it is telling us, so forget about, there's a factor of h squared, which is a factor of half. Don't worry about why it is there. So you can see that it says, the cold dark matter should be around 0.12, but that is half, so that's around 25%. And the normal matter should be around 2-3%, okay? But you have to, again, it's multiplied by half, so it is around 4%, okay? So this is how we get to this picture of what is the content of our universe, okay? So this is now, I want to show you this plot because I think this is a very beautiful plot. So what is shown in blue are actually the actual measurements, okay? You take your satellite, you point to the sky, you get those 9 maps, you combine them in fancy ways, and you measure this power spectrum. And when you do that whole process, you get this blue dots. And you take your model, okay? The red curve now is the model, and that's how exceedingly well it fits it. So if you take your data and subtract your model for it, that is, if this was in disagreement, then you would have said, the model is not quite fitting the data well, okay? So we have exceedingly good proof of how well we can, of how our universe works. So this is how we basically get to this picture. You do this whole analysis, and we are now able to say that, okay, we have this much dark energy, this much dark matter, and this much of normal baryons. This is where the story comes from. Okay, so what does this mean? So this is just one of the measurements, like I told you. So this is the way things were many billion years ago, 13.5 billion years ago, to be precise. Okay, and these tiny fluctuations, basically there were places where there was less matter and the places there were more matter. Now the places where there was more matter obviously collapsed to form the largest gravitational structures that we know today, like our Milky Way or the largest galaxy clusters that we've seen. And this is now this is no longer, we don't have to imagine this because we've mapped it. And this is actual data, but only on a slice. So the reason you don't see anything over here is because we sit in a galaxy and we cannot look through our galaxy. So there are regions of the sky which we cannot access when we measure in optical, but you can look up and you can look down. Oh, sorry. You can look up and you can look down, and that is what you see. And this is something, this is going further back in time in the universe, or in what cosmologists like to use is the language of redshift. And basically what you're seeing are, these are clumps of galaxies that we observe in the universe, okay? So all these, so this whole structure, all these clumps that you see are galaxies and how they are gravitationally interacting with each other and their state as it is today, okay? So these tiny fluctuations in matter actually seeded the growth of these larger structures in the universe that we see today. So the current model of the universe is basically then composed of a picture like that, okay? So we are somewhere over here, okay? What we are mapping is this surface, which we call the cosmic microwave background, which is mapping the anisotropies in the very early universe. There's some funky thing, the Big Bang, if you've heard of it, that is what happened then, but we kind of know little about it. We have very many models, varying kind of models, which we've not been able to distinguish between. But once we form these anisotropies, we have an exceedingly good understanding of how these form into the structures that we see today, okay? So what's next? There's lots of things coming next. This is the Planck measurements are not the final measurements. There are these ongoing experiments. This is already in operation. There are things that we are proposing now to make measurements for future. And across different countries. So these are in the US. These three are in the US. There's a potential idea of a CMB satellite being flown from India. We recently actually put an ESA proposal to say what should be our outlook in 50 years from now, okay? And there are missions from other countries, like this one. This particular one is from Japan, okay? And why do we need this? Because there's lots more we can do, but I do not have time today to tell you about it, okay? So I stop with that.
So thank you very much. So we now take questions. I will start with the first question. I'm sorry, I have the microphone already. So you talk a lot about the past. Mm-hmm. Can we also use this to predict, in your models, to predict the future? What's going to happen?
That does not operate on human timescale, so it's not the most interesting thing to do.
Oh, okay.
Sorry, because I actually had a slide somewhere. So humans have been here for roughly 6 million years. Okay?
I don't care about the humans, like future, like. It's fine.
Like, we know how to evolve this forward, so that's kind of trivial. The question, in a sense, it's trivial. What we really want to understand is how things happened in the past. That's what we really want to understand.
Okay. Why?
Why? Because, like, that's something you can go and test. From a science perspective, you go back to the circle. Mm-hmm. You want to model, you want to observe. Right? If you cannot observe and validate, then what use is modeling? Then you might as well do mathematical sciences, and you can predict whatever thing you want. You never need to verify it. Yeah, that's kind of what I do, actually. You never need to verify it.
That's my job. Okay.
Okay, but that's not strictly true. So one of the things that we worry about and that I've not spoken about today is this Hubble expansion, and so there's a lot of unknown unknowns. Like, for example, I don't want people to go away with the rosy story that we understand everything. The real puzzle is just this 96% of the universe, which we don't understand anything about. This is not a joke. These are two components of the universe of which we know. We know that this component should behave in a particular way for our model to be consistent with observations. So we know the macro properties of what dark matter is, and we know what dark energy should do. This should make the universe expand. This doesn't interact with light. That's what we know about it. We don't know much more, okay? And then there's dark matter, which again interacts gravitationally, makes stuff stick to each other, but we do not see it through light. Our challenge is we only see the universe through how matter reacts with this 4% content 4% baryons or normal matter that light can interact with, because the only way we see the universe is through light. And we can infer the presence of these quantities by the way it impacts what we observe. But we do not know what these components are. Right now, a lot of active research is in trying to figure out what these two components of the universe are. Okay?
Cool. So Danielle first.
I have a question about so how you built this initial
Mm-hmm.
You had these different wavelengths that were used.
Yeah.
That then ultimately brought you to this.
This picture?
No,
The angular power spectrum, okay. This one. No? Okay.
So, yeah, where you actually like
Ah,
build the,
okay. This one.
yes.
Okay.
Okay. So here you see, in the center of all of these, I guess this is the universe.
No, the Milky Way, our galaxy.
Sorry, the Milky Way is here in the center, and it looks like it's some kind of is it disrupting your ability to see beyond it? Like, why is it that in everyone there's a line, and now the line's gone in the middle? Like, how did you get rid of that?
So actually, it's not strictly true. There is a smiley, very tiny. If I show you on my laptop, you can't see it so well over here. But there's a tiny percentage of the sky in the very center, which we actually don't measure.
Okay, that's what you can't see it.
You cannot see it actually. And actually, when we do the analysis, like for the power spectrum or something, you would throw away large chunks of this data. You would not use chunks of the data very close to the galactic plane, because we are not sure how robustly we've removed the contaminations. So the analysis is done by excising large sections of the data.
Esha.
Yeah, so just a little bit of my philosophy. I know it's very difficult to answer, but I mean, first of all, like, is there anything outside the universe that we know? And second, like, the universe expanding, but expanding in what? Like, I mean, just like, we are expanding, but
yeah, it's. Let me try to see if I can answer that.
Oh, sorry. I forgot about
what
that.
is the universe expanding into, and
what's outside the universe?
what is outside the universe?
Outside the universe.
Right. So again, if you think of it in terms of, so there are two answers to it. So there are models in which you build, there are fancy models in which you expect the universe to be much larger than what we can observe. But my personal take on it is that if it's not observable, it's not, in a sense, relevant to physical sciences. Because the whole idea of science is that you observe, you model, you validate. If you cannot validate an idea, then it is not particularly interesting to science. That's one take on it. Having said that, it's not that such studies are not done. So like even with Planck, when we did the studies, you study for, so we typically, the model of the universe assumes that this sky is homogeneous and isotropic. What those terms basically mean is that this field has the same statistical properties no matter where you're looking. Now, this may not be true if you live in a universe where there are other universes. But they need to be tuned in a very fine way for that to work out. And to the best of our knowledge, we have not found any such deviations in this map. And this is our measurement of the universe on the largest possible scales. There's no way, currently we don't know of ways where we can measure beyond this surface, so to speak. Okay? I don't know if that answered your question. And what is it expanding into? I think this is a misconception coming from believing that it's an explosion, like you would have a cracker exploding and then it explodes in space. That is not the idea with the expanding universe. So the way maybe to think about it, if I can get a little technical, is let's say you want to define distance between 2 points. Okay, so you would put a scale. But let's say now I told you that the scale varies as a function of time. Okay, so the way we are doing this here, what we mean by the universe is expanding is everything is expanding. There's nothing that it's expanding into. It's just that the definition of the distance between 2 points is altering with time. So when you think of it from that perspective, you would probably not be worried about what is outside the universe. Okay?
Oh, that's cool. So, yeah, you were first. Yes.
Yeah? Oh, right. Okay, so it's actually,
The question?
this is something that I meant to look up. I think Planck, Max Planck, isn't he originally
he's
from Kiel,
German.
born in Kiel actually, right?
Yeah.
He's born in Kiel, so it's an electromagnetic spectrum, which is characterized by one number, which is the temperature. Okay, and for each temperature, there is one unique spectrum. So that is the two. If you take two spectra for two different temperatures, they will not intersect at any frequency. I don't know if I can describe it much better than that right now. But it has origins in Kiel.
Yeah.
No, it's one of the simplest. Any hot body which is in thermal equilibrium will emit only as a black body. For example, if you looked at the spectrum of the sun, it's very close to a black body, but not quite, because it has some absorption and emission that come from the elements inside the sun. I don't know if that helped, but if you go and look at the spectrum of a sun, it's going to be having the same shape like I showed you over here, but corresponding to around 6,000 Kelvin or so.
I think we were good with the Kiel. So, Neha? Yeah.
So I have a question. You showed that you made this model,
Mm-hmm.
and then it kind of fit the real data pretty well.
Mm-hmm.
But what you can see from the figure that you showed, that there is some discrepancy, especially in the beginning.
Yes.
But then it goes away after a certain point, and then it fits like really well.
Yeah.
So my question is why?
Good question. So again, this is something that a lot of theoreticians spend a lot of time modeling, but it's also there's something called cosmic variance. So when you talk about error bars over here, there are two types of errors that we have to worry about. One is the noise that the instrument adds, okay? And the other noise comes from the fact that we have only one universe to observe. So when you make a map of the sky, there's only one map that you can see. And when you go to these really low multipoles or large wavelengths, there are few modes that you can measure. And because there are few modes that you can measure, these error bars are actually quite large. And if you ask statistically, is this deviant? This is not statistically deviant, though it might look as though it is. If you ask statistically, rigorously, if this is deviant, it is not.
But then why is it so nice after a point? Like what's changing?
Oh, no, there's nothing changing. It's just that over here, you can have larger statistical fluctuations, because the error bars are in principle larger and the error bars are non-Gaussian when you go here. But when you go to these higher or the smaller wavelengths, these modes become more and more. So your error bars are become better characterized by just one number, the variance, whereas here that is not the case. These are skewed distributions. But yes, not to say that it has caught attention to a lot of theoreticians. There are many papers which have worried about why is this particular mode this slow, and people have tried to construct models to make this red curve bend a little bit so that it would cross through that. But the issue is that even though you can build such models, we do not have ways to validate them because it might fit this data point. But the question is, going back to the slide on the model, one of the important key factors a new model should have is that it should have a prediction. It is not interesting to me if you give me a new model and it tells me everything that the current model does. You need to give me something new so that I have a way to invalidate your model. Like I think there's a saying by Karl Popper, you can only disprove models. You can never prove them. So if you don't give me any way of disproving your model, it's of limited interest.
Okay, more questions. Yep.
Yeah? 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 This picture? Like, maybe I don't understand your question. That's old. Okay. Okay. So so the point is this. Light travels at a constant speed. Okay? So let's say the sun went out today, right now. Like maybe not right now because we are at night, but let's say tomorrow morning the sun went out, let's say at 10 a.m. You would not know about it till 10 or 8 past 10 because it takes about 8 minutes for the light from the sun to get to you. Okay? So the way we look at the sun right now is the way it was about 8 minutes in the past. But that is because the sun is only so far away. Now, if you think about looking at this surface is 13.5 billion years away. So the light that we see, this light that we are seeing, is something that is a remnant from that epoch. So when we map it today, we get a picture for what it was 13.5 billion years ago in the past. So yes, we are kind of time travelers.
So why did you pick the 13.5 billion?
Oh, this is again one of the things that you can fit in the model. And it turns out that when you do the calculation, this number pops out. So it's not a prediction. It's like it's a model, and this is a part of how we interpret. This is what we know about the universe now.
Okay. And you just keep adding it.
No, it's like, so if you...
I mean the other billion years.
I'm sorry?
Yeah, but you have to wait a billion years for that.
That's
Yeah,
true.
yeah, okay. Yeah, I had
Every year there's a little mark. Sorry.
Yeah, I think I actually had the slide which I did not put in, but the thing to put in context is how long have humans been here? Humans have been here for 6 million years. Okay? Not humans, actually. Humans have been here for 3 million years. Life has been around for maybe 6 million years. Now, if you look at what fraction of that is of 13.5 billion, you get the answer.
Okay. Any more questions? Yo, Deepa?
Mm-hmm. Right. It's actually much hotter when in the past. And that is why when we say it was much hotter in the past, and I was telling you that all matter is in the form of plasma, is because every time a neutral atom forms, there are photons which are energetic enough that would immediately ionize them. Okay? So it was very, very hot in the past, hot enough to keep matter in an ionized state. But today, because, again, of the expansion of the universe, and like I told you, the scale is expanding, so actually the wavelength of light also expands, okay? So the temperature has cooled down as a consequence, and that is why we see it today at 3 Kelvin. So one of the things that people have done is, through some other observations, sophisticated ones, you can go and try to, so basically, you can measure other astrophysical systems, which are not as far away, but somewhere intermediate, and you can ask, what is the temperature of the microwave background then? And it evolves in accordance to what we expect it to evolve. So let's say you look at it 8 billion years in the past or something, you expect it to be something like 15 Kelvin. And these are not accurate numbers, I'm just making them up right now. But these studies have been done, and people have actually measured this temperature evolution. So as you go forward in time, it will become cooler, yes. 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 And then it will disappear completely. What do you mean by disappear? It will just keep getting longer and longer in wavelengths. Flat, right? What do you mean by flat? Like there is a photon and there's a wavelength and you can keep expanding it, yes, into infinitely into the future, yes? Yeah. Does that mean it will be a loss of information? Oh, that's a whole another topic. It's
For another science night.
Yeah, maybe for another science. So, since you brought that word up, maybe you should Google it. There's something called the information loss paradox. And it's related to with a whole lot of fancy things with black holes, but... I was wondering, if there was some emission coming outside the boundary of this map. This is not an emission. Maybe I should make it clear. This is not an emission. There is a sea of photons, and it just happens so that at some epoch, the universe has cooled down enough that the photons can freely travel. It's like, think of it like you're in a cloud and you're outside a cloud. If you're inside a cloud, why is it that you cannot see far off? Because okay, let me not use words like optical depth, but basically light cannot travel very far because there's a lot of matter to interact with. But outside the cloud, it is freely traveling and you can look very, very far. It's exactly the same thing that's happening over here. So when you're in the hot, dense plasma phase, the photons cannot travel very, very far. But when it cools down and you have neutral atoms forming, then they have a clear vision and they can travel very far without being obstructed.
Esham.
Yeah, so if we just continue to the future regarding the time scale now. So we're gonna continue going until at one point it will just reach 0 Kelvin, so to say, and it will not go more than this. Like it will not expand beyond this, right? Or I mean, when it's reached the coldest point it can reach, what's gonna happen after, according to the models we have?
Like, we don't know. Like what? Let me think about if there's a good response to that. If you just project infinitely into the future, what happens to the universe? Yeah, I do not have a good answer to it.
Could you please go back to the pie chart?
Pie chart?
Yeah.
Yeah. All right.
Yeah, because these measurements seems to be pretty precise.
Mm-hmm.
How could we be very, very precise about something that we almost know nothing about? How do you quantify such things? Maybe you mentioned that already. Maybe
No, so how, okay, so you think of it like this. Think of it like a black box which enters your model, and you have to say, not black box. Let's say it's a constituent which enters your model, and you have to say how much of the constituent do you need to observe, to model all the phenomena in the universe. So today I'm talking to you about only the cosmic microwave background, but there are many other observables, and you have to try to fit all of them. When you have a cosmological model, you have to fit all of the observations simultaneously within the same model framework. Okay? That is the real success of the model. It's not about just fitting these observations. It's about fitting multitude of observations with the same model, and all of them actually give the same answer. Now, strictly speaking, I'm lying to you. That's not true, because when you measure actually the Hubble constant today, there's actually a mild tension that we are living with, and when you look at these early universe probes like the cosmic microwave background, and if we study stellar explosions, like stars exploding in the local universe, and we try to measure how fast the universe is expanding, we get two different answers, okay? And right now, we do not know why this is. So there are speculations of whether there are biases in the data, which we haven't understood, or there is something wrong with the model, so people are trying to correct models. So now the game is you have to tune the model such that you explain new observations, but without breaking any of the things that you already explained. So then that becomes very challenging because there are very many constraints that you have to worry about. But that still does, so all of these questions are not going to get to what these constituents are in themselves. For that, there are particle physics experiments going on. So people, where they try to detect new types of particles, and they're trying to see what this might be. We have no clue right now. Every now and then, if you keep following news on science, you'll say, oh, we found something, and maybe this is the dark matter particle, only to see that it fizzles out in some time. So as of now, to the best of my knowledge, we don't know of any particle that we've detected in a lab that would constitute this or that. Okay? This is all ongoing study. These are, in a sense, big holes in our knowledge, and this is something that the coming generation of scientists will be hoping to fill.
More questions? Yeah. Okay. No more questions. You can talk after with a beer that you throw away. So I just want to say, everybody, thank you so much for being here. It's real nice to kind of go back to this science night. Sorry. And I hope to see you next time. I think the next time is going to be like in December or something. We still have to discuss. And we're going to try and have, again, very nice talks, very nice scientists, people that work in Kiel, maybe not. And then you do not, but now you are here. So, yeah, hope to see you soon. But follow Anza on Facebook and stuff.